Hello everyone, I'm Lara from Proxima, and today I will host this embedded working group. Please write your name on the attendance list in the agenda. Okay, I have left the link just in the window message. And I would like to say that it would be fantastic if someone has personal, professional micro ROS projects and want to present it here at the embedded working group. In this case, you can write me an email and when we can talk. So let's get down to business just now. At our last meeting, we had Yasushi Sohi, co-founder and CEO of Space Cubics, and he introduced us the world of Zephyr modularized with a micro-ROS version. And also, Russell Joyce, a robotic and embedded system research engineer at Microsoft, provided an overview of Microsoft Research Project Silica. And for today, we have here Braden Wagstaff, a computer and robotics engineer from ARK Electronics, and he will share a demo of the integration of ROS2 and PX4 through micro uXRCE-DDS. So, Braden, is your turn.
All right. Thank you so much for having me here today. My name is Braden Wagstaff, like Laura said. I'm a computer engineer at Brigham Young University. So this April, I'll graduate with my undergrad. And this past summer, I began working for ARC Electronics up in Salt Lake City with Alex Klamai. And so what ARC Electronics does is we create hardware for open source projects, specifically PX4. And most of the hardware or most of the projects that have been done by ARC Electronics have been very housed around PX4. That's all it's really done until recently. We released the Orin Jetson Nano, or NVIDIA Orin Jetson NX or Nano PAB, which can house a PixHawk flight controller in it, which means that now on a device you can have a running Linux computer connected directly to a PixHawk flight controller, which is really, really powerful. But in order for that to work, you need micro DDS. You need uXRCE-DDS in order to connect those two pieces of hardware. To connect those pieces of hardware. And so what we're going to look at today is a demo that I made over the summer to be a starting platform for people to create things with within this ecosystem of products. And so if we jump to here, okay. We call it, I think the name that was coined was the Cyberbot, maybe the Cybertruck. Mainly because it is a little reminiscent of Elon Musk's Cybertruck. But this, if you can see my mouse on here, is equipped with a LiDAR. You have two RTK GPSs, a depth camera. There's an optical flow in the bottom of this. And in the middle, you have the Jetson Nano. And on the underside of that, you have a PixHawk flight controller. And specifically in here, we have the ARC V6X. And we're using micro DDS to connect those two, and we're able to do some really fun stuff with this. This right here is a quick draw up of the architecture of what's going on here, and we'll go into a little bit more detail as we go on. But at the center of this, we have micro DDS connecting our PX4 side of things with the ROS side of things. And before we move on, I'm going to show a little clip from the commercial UAV expo in Las Vegas, where Raymond Roche, he interviews Alex, and they talk about what they've done with the Cyber Rover and the implications of it. If you can't hear the sound in this video, please let me know, because the background music is a little loud, and if you can't hear anything at all, we'll just move on. But please let me know.
Hey, we're here with ARC Electronics, and he's got his new rover with the new Jetson carrier for PixHawk. Yeah, can you tell us more about your build here?
Yeah, so this is my demo rover platform that I've brought just to show my products, and I've got My big product here that I'm working on now and getting to market is the ARC Jetson Pixoc Autopilot Bus Carrier. It's a mouthful. I don't know what else to call it. It runs an ARC V6X flight controller in the.
Oh, nice. We love buffering.
Pixoc Autopilot Bus form factor, and that's on the bottom of this board. You can see the micro SD for the logs sticking out the bottom. Then you've got the NVIDIA Jetson Orin Nano, or the Orin NX on the top. This is an Orin Nano, and I have a drone with the Orin NX. So that's running Ubuntu, NVIDIA Jetpack.
Let's pause right there. So you got a Pixoc
Yep.
flight controller, latest V6X generation. You got a Norin NVIDIA chip.
Yep.
And you got a carrier board that's connecting both of them, and you got them hooked up through USB high speed.
Yep.
Super speed.
They're actually hooked up through USB high speed and UART. And this setup is actually running everything over micro DDS over UART between the Pixoc PX4 and ROS and the Jetson, and then that's all piped back to the Steam Deck for controls. So ROS running on both ends, controlling PX4 set up in a rover airframe mode.
Talk to us about the sensor set.
Yeah, so this actually has as far as the flight controller side of things, it's got dual RTK GPS, the ARC RTK GPS. It's got an ARC flow on the bottom for measuring distance and velocity, pixel flow. And then it's got hooked up to the Jetson on the Ubuntu side, ROS side of things. We've got the SlamTech rotating LiDAR. We've got an NVIDIA or an Intel RealSense depth camera. Those are connected through USB to the Jetson. And then we've got dual ARC power modules running in parallel for 2 batteries and 2 5-volt inputs. The Jetson carrier takes triple redundant 5-volt power inputs, so you could have up to 3 5-volt power inputs for a max of about 80 watts input, depending on what you have connected to the Jetson carrier. That can scale for your needs, or if you lose one power module, those are set up to fail over gracefully. Yeah, it's I've kind of designed this as a general purpose, robotics and drone development platform.
Awesome. Can you talk to us about the Steam Deck? I think that's something that everyone wants to hear about.
Yeah, the Steam Deck made for a convenient development platform. It runs, Arch Linux. We got Foxglove running on here, thanks to the Foxglove CEO for getting a flat pack for us to run Foxglove on here. It's currently not connected, but yeah, you get sticks, you get triggers, you get the point cloud, you get the camera, you get battery status. Yeah, Foxglove is it's a great setup for doing development, and with the Steam Deck, it's even easier. It's for the price, it's a great platform.
Yeah, and since we're here.
Move on, click. It won't go. One moment. No. There we go. Okay, so that is the general overview of what we created over the past few months. And some people might say, there's a lot of conversation about the implementation of micro DDS and when it's necessary and when it's not necessary. Because if you just wanted to build a rover, it's very possible that you wouldn't need any form of Pixoc flight controller, because you could figure out most of that stuff on the ROS side and negate the need for any kind of middleware for UORB messages. But the moment that you take a platform like this and you put that on a drone, that's where ROS has not really gone yet. And if it has, it's with the help of either like PX4 or RGPilot. And when you do that, you need micro DDS. I personally don't have a lot of experience with PX4. When I jumped onto this project, I was basically all on the ROS side, and I was amazed at how easy it was to interact with PX4 because of micro DDS. By just booting that up in a terminal and then bringing in all the UART messages, I would just see everything on the PX4 side as a ROS topic. And that was fantastic. It was so nice. And that really converted me to just publisher subscriber, the pub sub architecture. And I think it's a great feature of MicroDDS, being able to just port things over like that. I also like how, at least within PX4, it isn't going to transfer every single thing that happening on the PX4 side of things over, because that's just a lot of bandwidth. And so there were some things that we needed, for example, like the state of the battery and its voltage, that isn't by default available on the PX4 side of things through MicroDDS. But it's very easy to go in and change the YAML file, defining what will be published over MicroDDS. And so it's really customizable and really, it's really, really great. And I should have moved the slide on why MicroDDS. It's because, wow, come on, there we go. It's because ROS2 and PX4 are both very powerful, but using them at the same time is rather difficult. And so with something like MicroDDS in the center of them, it's almost like they were always meant to work together. It doesn't feel like you're working on two different platforms with MicroDDS in the center. It's just one big development platform. And I personally really liked it. I enjoyed it. And so this came about, this came about when, in the beginning of this project, before we had any of the hardware yet, because the Jetson PAB was still being manufactured, I set out to figure out how to merge PX4 and ROS2. And there are a few tutorials online that talk about it, or maybe they show an example of what they did, but there wasn't really a definitive example for a complete beginner to jump in and use both of these things together. And so I went out and I made one. And we're not going to look at all this, but a huge part of this is basically to use PX4 in offboard mode with ROS2 is just setting up the MicroDDS portion of things. And so in the end, we'll jump towards the end here. In the end, this just controls a drone through teleop inputs. Keyboard inputs come in on the ROS side of things, and then those get published as a twist command that then goes to over MicroDDS to PX4. It's pretty simple, but this entire setup is, I mean, it's a 16-minute video, and a lot of that is me giving you the things to copy and paste in. So there's still a lot to be done on making knowledge like this more accessible and easier. And at the heart of it is MicroDDS connecting these two things. It's kind of like the hidden player in the background. And so after we figured out how to easily connect ROS2 and PX4, flip it into offboard mode, and control it how we wanted, the next step was moving away from the keyboard teleop controls. And this is where you saw in the last video, we figured out the Steam Deck. And so the current architecture on here right now is on the PX4 side of things. We basically have, you have the arc flow, which is the optical flow, 2 RTK GPSs, and then the IMU within the flight controller, and those will all help with odometry. And all the data, they're all passed into the UORB topics, or passed in as UORB topics into DDS and passed right to ROS, and now they're just available. Sorry, gonna take a sip of water. I'm talking a lot. Those are all passed in and are available on the ROS side, and now they're just available as ROS topics, and you have access to all that data. And then on the ROS side of things, we have the RP LiDAR A1, and that's being published using a node that we created. And then we'll talk a little bit later about how we implemented the RealSense depth camera using NVIDIA's NV blocks and Visual Slam examples. But the video out from the RealSense camera goes, and that's kind of a squiggly line, but it goes down here to the Steam Deck and goes into Foxglove. And on the Steam Deck side of things, it got a little bit funky because Steam Deck runs Arch Linux. And in order to run ROS on there, if I understand what happened correctly, I don't think we could even use Docker on Arch Linux. We had to use DistroBox, which I think is another form of a Docker container. And so we had to use a DistroBox container running Ubuntu 2204, which could then have ROS Humble, which could then have Foxglove, and I didn't actually put it on here. So I think Foxglove would work on anything once you get the flat pack from Foxglove. Sorry, the words. But what I neglected to put on here was the Foxglove bridge, which actually connects all the ROS topics to bring in a Foxglove. But we also needed to run a DistroBox Ubuntu 2004 container of ROS Galactic because that's what was running natively on the Aura Nano. And so the joystick inputs were leaving the Steam Deck going over Wi-Fi to the Aura Nano. And the Aura Nano we had set up to just broadcast its own hotspot that the Steam Deck would automatically connect to. And so what this allowed us to do was we could just boot both of them up. They would automatically connect. We run the one launch file on this side. It automatically runs on this side as well. And you can arm it, drive it around, and you get the video feed in, which was a really, really nice. It was a fantastic development platform. Setting up the Steam Deck was a little difficult, but once that was set up, it was amazing because I would just HDMI into the Steam Deck and have a keyboard and mouse, separate monitor, and just develop all on there. And then when I wanted to test it, just unplug it and use it. And I've never really experienced anything that smooth before, and it was really nice. So I know this is a presentation about micro-DDS, but I want to see more Steam Deck development out there because it's fantastic. I love it. And so here, oh, yeah, it's all happening there. I'm not quite sure why I put that circle there. But if we move on to a deeper example of the Steam Deck, we'll see a little bit of this. Our setup on the Steam Deck and Foxglove, we have our camera output, our LiDAR point cloud. We can see we're at about 25% battery, and we can drive around, see our point cloud changing, and go up to the dog. Hey, buddy. Oh, big stretch. Yeah. And then if we go outside, we can actually see it driving around. And so in this example, I mean, to go back to, gosh, slides. Hold on, there we go. If we go back to here, so all the commands from the Steam Deck, it's just sending twist commands from the joystick to ROS, and then ROS is jumping over micro-DDS to send the exact wow, the word is escaping me, but it's sending the commands to PX4 over micro-DDS. And so we have all these different connected things, but they all work together to make a nice little demo where you get the LiDAR point cloud and the video in, and it works really, really seamlessly. And so the final culmination, or the final goal for this project was to put all of this onto a drone and make it autonomous. But we thought it'd be safer to develop first on a rover. And so the goal at the end of this was to make a rover that could map an area, perform a SLAM algorithm, and then use nav2 on the ROS stack in order to navigate. Sadly, the summer ended, and I went back to school before I could finish that. But hopefully we can get that up sometime soon. But what we were able to do is we were able to implement the NVIDIA NVBlocks and Visual SLAM example. And this is some really, really powerful stuff. I didn't have enough time to really mess with it, but from what I did see, when implemented correctly, you could do some fantastic stuff with this. NVIDIA Isaac ROS, it's designed to work on a Jetson Nano, or on a Jetson Orin with a RealSense camera. And so we had the full setup that was needed in order to run these examples, and they really were rather amazing. Let's jump, nope, okay. So look at this. You don't need sound on it. So what we're doing, we're driving around and we're actually mapping the entire area, and it's also performing a slamming algorithm at the same time. And so this is implementing their visual slam example, and also NV blocks, which is all of this, not just it's not just a point cloud essentially, but it is a, oh, we don't need Slack open. But it is giving the full 3D map with the voxel blocks throughout the whole area. And I was absolutely amazed by this. It worked so seamlessly and so well on the Jetson, and I'm really excited to do more with this. The next step from here would just be able to take this and implement nav2 in order to essentially, set a pose estimate and set a goal pose and have it go wherever you want it to go. And like I said, we just ran out of time, and I'm back here at school taking robotics courses, but I'm not working on this right now. So if other people want to take up the charge and jump more onto this, I would love to see more of it, because I think with just the power that we have on an NVIDIA Jetson, there's some great opportunities for development and to make some really great products and demonstrations. But that is essentially the end of, let's see, that's essentially the end of the presentation here. We have PX4 connected to ROS, connected over micro DDS on the Aura Nano, also connected to the Steam Deck with teleoperation and video streaming. And we also can perform a visual slam and NV blocks algorithm in order to visualize where we are in our surroundings. That has a potential in the future for better navigation and nav2 implementation. And hopefully we can get this onto an aerial drone platform and create some more autonomous examples. But that's the end of the presentation, and I'm open to answering some questions.
Yeah, I have one question really, but first of all, thank you very much for this presentation. This is awesome to see uXRCE-DDS in this little spot of this super big demo. That is incredible. And also, I didn't know that you can use PX4 for running on rovers. I thought that this was only for drone, but really nice to see that. I wonder if also the controlling of the motors in the rover is handled like forwarding the teleop topic to the PX4 system, or this is done autonomously mostly by PX4, or how do you handle like the power that the motors have in the rover and the direction and everything?
Yeah, that's a good question. So PX4 rover is still in development because not as many people use it. It's not as fleshed out as it is with drones. But on the PX4 side, essentially PX4 really thinks that it's just getting joystick controls from a normal controller, and so we just convert the Steam Deck controls just into X and Y values, and it just sees X and Y values and assumes they come in as RC controls essentially. And so if we implemented nav2, if I understand right, we'd have to write, I think, I don't know if that sounds on my side, but if we connected it to nav2, we'd have to essentially make an algorithm that could map basically like direction or goal estimates to what the PX4 controls would be. That was the next thing I was going to do, and then I just ran out of time. Did that answer your question, Pablo?
Yeah, understood completely. Thank you very much one more time.
Yeah.
Other question? No? Okay, so thank you very much, brother. Hopefully someone will continue with your work. It's amazing. And okay, that's for today. I hope to see you here in almost 1 month. Okay, see you. Bye. Again, thanks, brother.
Thank you.
Bye, thank you. Okay.